Okay, so if there are no more questions, let's thank the speaker again. We will speak about the. Okay, so thank you very much for being here, and thank you for organizing providing this great workshop, p-adic Hodge theory. So today I'm going to talk about works in progress with Johannes Anschütz, Guido, Bosco, and Arthur-César, and Johannes Anschütz, Guido, Bosco, Arthur-César, and Scholze. That includes this theory of a piece of this well, the theory we've been like advertising for a little bit of this analytic prismatization. So this theory of Fargues-Fontaine de Rham is going to be a very important piece of that. So let me start with a derivation that actually I didn't knew I was on using. Right? So let me start with properties. Right. So let's fix speed, right? So we have different cohomology theories floating around in the p-adic geometry. Let me maybe just specialize it because diamonds. So for diamonds, with spaces, perfect spaces, and things we have of them, or perfect spaces, I would say. We have a or L different from P, some cohomology theory, which are just usual psychomology from L cohomologies. L, P, L. There are first in the realm of adic spaces developed by Huber, then extended to both diamonds, by Scholze. Okay, this is a bad conference, so I'm not going to talk about that. Instead, let me mention this almost multi-box theory of Lucas-Mann, which is a theory of solid almost hopeless modules and diamonds and perfect spaces that, in a precise sense, is an improvement of FP cohomology. In the sense that actually FP or a large class of FP et al. Groups fits into this theory perfectly if you construct it carefully, for a way. And that, well, the 6 operations you have here, and you have very strong 6 control components. So this is the thing you like, 6 control components. So following the work of Mann, and joined with Anschütz and Bras, so they extended this almost theory to a theory of solid modules, not values maybe in O plus mod P coefficients, but more like in coefficients over a Fargues-Fontaine curve. So let me just write this and like hats in boxes. So this is some kind of order cohomology theory. It's Bras-Vezzani, which in this case, opposite of the tool of FP cohomology is an improvement of both, well, includes this one, and it's again like a large category of FP product sheaves or FP product sheaves, and gives a good 6 control formalism for this sort of commodities.
Actually, this also has an integral.
It has an integral version that's yes, I could write that's kind of almost floating around. Yes, there is also an integral version that you can replace. So, for example, in the analytic cohomology theory, it explains why when you look at product homologies or some random QP local systems, you get very huge homologies if you do it in the naive way. And the reason is because for proper smooth varieties. And the reason is that actually you should be looking at this if you actually want to get perfect. Just need to change the space. So regarding this last homology theory, let's say that take the stack the stack we like a lot, big one. We take this version. So this is some stack that parameterizes degree one device source of one fields of perfect rings up to Frobenius. Something that one can write. It's great. It's add the young diamond spectrum 2P modulo Frobenius version. And then something very good having of this theory is that you can, even though it is defined using very heavy machinery and very complicated spaces, you still can relate vector bundles on, let me say, deep one homology theory. Maybe take the rational version, well, with several things, and maybe after some intermediate steps, you can just go something that has been studied classically, but then follow a lot of other people, which I just didn't want. And let me put a decoration to these Figma models, and let me be a little more specific. Is that I want to get the Figma models over convergent. Again, is some classical logic that here from Camargo in the average too. So, well, somehow the most mysterious word for me here is proper ring. Okay, so let me try to say what is the proper ring. So we can start with a disk. Well, very bad drawings.
So, can I ask a question? So, so that the fact that cohomology derives, but how do you get rubber ink out of it?
Right.
Over convergence.
Right. So, well, let's say that at first, and maybe it's not too surprising, some kind of Figma modulus in some pure Fargues-Fontaine. Maybe you can go up to pure Fargues-Fontaine attached to the atomic extension, and then the passes to these rubber rings is work of Juan and Scholze using this sort of set theories in the completion by the vectors. So that's this where all these points are contained. Yes, a lot of papers and heavy points. But hopefully this would be a little bit more. I hope that this gives a little bit an idea of why you should expect this. So this is an open disk, which okay, you can write it down as the p-adic spectrum of just a T, and then this adic derivative over QP. Then you can start considering some neighborhoods of the boundary at 1. So for R, you get zeros for the 1. Let me just, this be the annulus of internal radius 1, opening a disk. This, the ring over converging row ring is well, you can take the global sections of each of these atoms. And then just send the boundary, the internal boundary to the external boundary. that's the rubber. Symmetrical is some kind of hidden boundary. The boundary, well, it's just somehow the hidden boundary of the open unit is close ghosts. Or yeah, as in here, ad hoc language is like a ghost circle in the boundary of the open unit. Yes. Right. But well, of course, the rubber ring itself maybe is interesting as someone with more structure. So like that.
And colimit literally means colimit in the usual sense, not in some.
It means in the usual sense, exactly. Yes. Yes. So now that we are Frobenius. Frobenius. So in particular, this is just a delta ring. The language we like is cohomology, just a delta ring. So then, well, because it's going to be a little Frobenius, it is maybe not too difficult to say that see that this Frobenius actually is going to, well, it's going to give you an automorphism of this continuity disk, meaning that it sends the boundary to the boundary, so it just acts in the opening disk. And then, well, maybe it's not going to preserve this analyte, but at least in the limit, it doesn't care. It's going to preserve it. It's going to expand it or contract it. So this price operator of Venus by on the world. Yeah. So examples of this, depending on the Frobenius, you may think that there are different theories. So let me just take the cyclotomic delta ring that corresponds to T to be 1 plus T to the T minus 1. But then we also have the Voigt in delta ring. So then, pi model. For ring definition is just that pi a module. So just a module with a probability which is semi-linear for the action of the rubber ring, which is finite free over R and M, such that the linearized Frobenius is Einstein. Okay, so that's the taking care of this equivalence. I just wrote the points that the action of pi. Well, let's say that the action of gamma. So cyclotomic ring. One can define an additional action of gamma. So gamma, right? Gamma is just a set cross, which is just the Gauss group of the cyclotomic extension. And for any element set cross, this action of gamma is just given by 1 plus TPA. And well, once you get this action, you can imagine what a phi gamma module is going to be. Just a phi gamma module over the rubber ring that is projective and linearized Frobenius extension. Okay. But actually, this rubber ring is not just a random ring. It comes from a ridge space, which is smooth. And ridge spaces, so we can take connections in ridge spaces. So the rubber ring has action. Maybe we'll say a derivation. Maybe T, maybe dt over T. So we can talk about like not just vector bundles in the rubber ring with an action of gamma or an action of A, but actually we can talk about flat connections. Just like flat connections. Flat connections meaning vector bundle with flat connections. I don't want to that thing. So talking about these flat connections is what well, maybe to say that the case of the cyclotomic rubber ring, well, you have an action that's explaining this morning of the Lie algebra, like derivations in these things. And well, if you pick like some suitable generator, you just B, just one. Just pick generator one. Then this derivation, this derivation is actually given by the derivation of the variable t, the rubber ring, after you multiply by log.
Okay, that's an action of
It's log of t minus 1 or log of t plus 1.
Okay, that's an action of R or
This is an action. Sorry, thank you. So at least if you start with a graphical module, you can get something that is close to derivation, but maybe guarantee that it's a derivation. You need to know that some kind of poles are cubes. So this leads to the notion of another module over the ring. And let's say that in this dictionary, that whenever you have like a representation that gives you some vector bundle in one or something like that, so then it produces for you a Python module. Then those Galois representations that for which this derivation can be promoted to a derivation of this connection, so I just can divide by this by a term of Gaussian, this is Gaussian, are precisely the bump representations. So this connection knows about being the round. Okay. So following this theory, so the initial I just got the B at the end. Is at the end? So for cohomology, the Q coefficients, we have this well, the theorem of Grothendieck, the monodromy theorem of Grothendieck, telling you that for such a Galois representation of maybe E with values in Q vector spaces, you actually can decompose it. Comes from the information of Frobenius, from the important operator, and some smooth action of the character. So the analog, or the p-adic analog of this monodromy theorem is what we call the p-adic monodromy theorem. That says that this is a theorem on the spelling server. And also known as group collector, but it can be rephrased in terms of this model connection. So it says that any binary module over a ring is what they call quasi-coherent. This means that there exists a suitable X variant finite without extension prime or ring such that this vector bundle with this prime connection, when you restrict it to this, is just an extension at least if you forget about the structure of Frobenius. So let's just forget Frobenius. It's just an extension of triplet connections. Just and using this theorem and maybe classifying what is the possible extensions of O itself in the rho ring. It was Garnier, maybe following a Courbat paper of wholeness. We proved that. So let me state the second case. So let's not the second ring. Then, if you look at phi modules with connection in the rho ring, that maybe have an additional action of the Gara group of gamma that is compatible with this. So this category is equivalent to a category of phi modules, some smooth action, P over QP and Hodge. Let me say what this is. So this CC, this means that the smooth action on an dimensional this Newton linear action. QP unramified vector space. This is just Frobenius, also like Frobenius. Frobenius, and this is an important operator that satisfies that if you apply Frobenius n, then this is just the same as n Frobenius. So this, because this is the kind of objects you can allow to classify in modules, is why value restricted is the analog of the actual monolithic, because this is what you end at the end of the classical monolithic. Okay, so what we're going to do next is mention how this theory of proper rings and fine modules by connection actually fits into this called analytic Rham stack. So somehow all these features are explained, or at least can be understood using pure p-adic over perfectly geometry analytic.
You can just explain, like, is this overconvergent thing the same as? Is that what you're talking
Yeah,
about?
the non-overconvergent thing is something that deals more with just this power series ring, and then you invert the
Okay, and in this equivalence, you can choose any local ring, or you have to choose.
You can choose any rho ring. Well, give me this action of gamma. Let's say modular action of gamma essentially working with one rho ring is the same as working with any other rho ring. Let me say it this way. This the category of phi modules with connection for a rho ring is independent of the rho ring. This is perfect connection. This is because of the gamma.
Juan, before you, so you really want to work with split QP and not split QP for AVA?
For this statement, I do yes. Okay, yes. Yes, because I want to see the Holger group of QP. Otherwise, I just would see there. Yeah, that's all. So for that, let me just briefly say what I did last time. Want to do the workshop, maybe I would to start saying that everything, all of this is happening in this category of analytic stacks of Scholze. maybe you're afraid of these words, or as what can say, just don't be afraid. And you can think about analytic stacks in the same way as schemes zero sense. In the sense that you start with rings. Then instead of jumping to schemes and the black spaces, the minimum prospects, or this other kind of adjective you put to any other geometric object you build up from rings, you just go directly to both stacks. So when we talk about stacks, that is just sheaves on the category of affine stacks, which is just the opposite category of rings. And for set up this theory, you need to work with so always the values in groupoids and vectors spaces. And this category of rings, it has a contour, which is the unit embedding that we call spec. So stacks is essentially the same. Maybe sheaves here is with black topology, then you know that. Stacks, it again just some kind of sheaves or some nice topology of analytic rings. Values in group points. And then you have a unit embedding that you just call an of course, like this is just purely categorical framework for that. Then there is geometric intuitions and geometric calculus logic, but at least categorically speaking, it's just the category of sheet. Basically, just think about scheme, not just not as gluing rings, but just values in rings. Then this, well, what is this? The Rham stacks. So I'm going just to mention what it is for each space, and then just the properties. So for each spaces, it's can give a construction. Is a Rham stack. So take the diagonal of X of 6. And then, well, the diagonal you can define something that we call this overconvergent neighborhood diagonal. That you can think of this as the intersection of open spaces. U, and if you just look at the shape, the structural shape of this space, and you compute, well, what is the restriction of the shape to this diagonal on its way, then the functions you will find, or the shape of functions, I should say, it's just these functions of the general functions around the diagonal. Just taking over convergent function around the diagonal. At least something that you can always do in classical language. It turns out that this guy here is an equivalent relation. It's basically measures 2 points whenever they are close in some overconvergence. That's what this equivalent relation is. And this is the Rham stack. Understood as the quotient of X under this equivalent relation. So maybe it's called the Rham stack is because there is a relation with the modules, and there is. Let me study the relation theorem. What is in Despacito. So, yes. And the theorem tells that the right category of this Rham stack is actually equivalent to a suitable category quasi-coherent decap models. Coherent models. It's where this decap, the sheaf p-adic differential operators was introduced by reason. The theory of the models in the varieties, by something called coadmissible models. And turns out that this theory just contains that theory and actually can give us explicit description of what it is potentially differential.
Possible to see what.
This hat corresponds to say that this is infinite order. So it's some sort of partial completion of the relationship with differential operators. That's what they have. What was the question? Sorry.
What is possible to describe this for the design?
All right. Okay. So in the case of disk, okay, maybe we'll do after that because really not going to be important for all. So, yeah. There is a bit of question on this, but yes. This is a filter demonstration. So this definition on this construction, so this is more or less what's happening. There is a actual definition, but which follows very close the classical definition of Simpson, taking some reductions and well, like some notion of bounded rings and some notion of elements of non-zero. Let me not go into these technical details. Instead, let me just give setup at least a box of tools that helps to compute these round. So at least for rigid spaces, we know what they look like. Maybe this equivalent need to be smooth for the right hand side. Makes sense. For smooth rigid spaces, for instance, there may be something to say. So yes. That you take the round stacks of distance, morphings of smooth morphings of rigid spaces. Then this, the structural shift, so it looks like that. This is relative to round college. This is an object that computes round homology in particular, but of course that has a p-adic frameworks. Right. Okay. Is there any question?
Sure. This intersection, can you convince me it's not just delta x again?
Yeah, it's just a colimit of rings. Because the intersections.
Well, you're intersecting not rings. I mean, you're intersecting having spaces here. And what categories is happening here?
This is happening in different stacks.
Rings.
And okay, let me say that if this is happens. Oh,
So Jared, it's going to be like an open convergent ring.
Well, you know, I'm rather happy with the definition of O delta x.
well, I mean,
It's like the diagonal as a topological space equipped with a funny structure sheet, like some structure sheet.
Yeah, the underlying topological space of this, I hope, is just delta x.
yes.
Yeah, okay, good.
Yes.
Okay, so then, okay, so we're considering an equivalence relation in this category of maybe ring spaces.
Yes.
And that's what this.
What's this quotient is? Yes. But yes, that's a problem. Like the underlying space of this thing is the same delta x.
Yeah.
In the shape of function what changes.
Is the reason that you don't actually complete this intersection, right?
right, I just taking the intersection, but not the completed intersection. So this is something that's going to happen a lot. We want to decomplete by not taking completions. So, well, let me just give a bunch of the minimal definitions of things that will imagine spaces. So first, maybe let's take the A is just a coordinate. But across with the coordinate. Then its uniform completion is uniform, and you can take the coordinate of the bounded elements of each Banach algebra, our bounded elements, then the P complete. This is a usual construction that we do, for example, when we take limits of any spaces that give rise to perfect spaces. Usually, this kind of coordinate. So given A of this form, so A, coordinate algebras. For some technical things, let me just introduce this notion of probabilities of separable simple analysis. If maybe it is a circle, then a circle is just a coordinate spot of a circle. This tells you that this guy, at least in some uniform completion, it can just be approximated by controlling any values. For example, this is just going to be a this is just going to be a Banach ring. So this is the same as saying that this one is one of the bases. Finiteness condition. This.
Banach physics.
Then to recall what the thing is. So there is in the technology of diamonds this notion of a strictly totally disconnected perfected ring that you can just let me just recall what it is. A is strictly totally disconnected. If maybe I'm doing a slightly different version where I don't care about a plus, just care about the ring. If the problem holds, so first A is a perfect ring. Good. Second is that, well, the underlying topological space of the perfect ring should be defined. So how do you say that? So usually you can take a span A at some plus, then you take a circle. But this one is not it's some kind of non-Hausdorff space. So let me just take a whole definition. This is what is called the Berkovic space for that. I'm just going to ask that this is provided. Something very good about this kind of spaces is that for any Banach algebra, in the product there is a product cover that looks like that. This one forms a basis for the product topology of any Banach algebra.
What is the term you do? What is the ontology? That is
Sorry, sorry.
for what? A is.
A is just strictly totally disconnected. Yeah, sorry. And finally, well, this is just totally disconnected. And before strict is that for all points of the vector space, the residue field of the perfectoid is algebraically closed. So I'm going to immediately erase that board because I actually want to keep this thing safe. And then, well, again, as mentioned that this analytic Rham stack is something that you can define not just for Regis spaces, but you can define for any analytic stack. In particular, you can start defining these things for this kind of rings, for perfectoid rings or just arbitrary adic spaces. And then you may wonder, how much descent do I have for this stack? How much the Rham cohomology cares about having differentials or not? It's just a purely topological right? In some sense. So let me state a theorem that maybe you should call the probability theorem.
Why do you have this condition as how does it work?
This condition is something that could look topologically, but actually is a deprived condition that I mean. It's something technical just to have access to descendable, some kind of nice presentability properties of the sense of factors. Yes, so somehow, even though it looks topological, it's more from algebra. So then complete theorem of the stars just to do that. You're working on that. So let A be one of these spherical coordinate algebras. And what this theorem is going to tell you is how to compute Rham stacks. At least if you know how to compute them for Regis spaces. That's the goal of the theorem. So the first thing is that, well, again, this is just notation, meaning all of these stacks attached to this ring. And the Rham stack of this ring actually only depends on the uniform component. There's only variant that is, I mean, can take whatever column you take, and it's going to have the same Rham stack as completion. So, thank you very much. Maybe the second one is that there is quite a lot of cover B by strictly totally disconnected separable algebra. Such that the Rham stack of B mapping to this Rham stack of A is a surjection. So this means that actually you can recover the Rham stacks from perfectoid space. It's good. And note that this one does not have any differentials. So kind of surprising, you can still recover B modules for Regis spaces from something that has no differential function. And maybe the last one is or is that, well, you may ask, okay, this is just only the locally you can work for that, but how about descent, actual descent, or V descent, or probable descent? So there are some partial results, or great results. The morphing perfect rings, or B over perfect rings. And recall that here I'm not using A plus, so I'm just looking at everything as, let's say, the minimal compactification of all the spaces. So all these rings are just over QP, and I'm not taking any sort of additional adic spaces. So this actually, V cover would essentially means that the recovered space suggests only this sort of recovered space. Let's say for this, I don't want to involve that. Then there are two cases. Let's say V is a quotient of perfectly bold. Or B is a countable coordinate. With A to Bn being état maps. right? So something that is kind of volatile, but maybe we're controlling the size. Okay. So then, this map to this map is a surjective. So what is this telling you in practice? In practice, it's telling you that, again, the Rham stack don't care about completions. You can always recover the runs of perfectoids. And, well, maybe the first one you can make a little aside, but the second one tells you that the Rham stack is well defined for diamonds, at least as long as diamonds will take it in these more like Berkovich-like sets. Because you still can model by equivalent product equivalence relation, at least countable ones, so kind of family of diamonds, and you still have descent of this stack. So you can make sense of the stack.
So discover you got in point 2 with some kind of
yeah, you can start building hypercovers of that, yes. But kind of the idea is you have the Berkovich space, you first do, I think what happens with this construction is that the Berkovich space is a compact tabular space, and this one you find a covered by a profinite set. And then you translate this covered by a profinite set into the ring, and this gives you something that is going to be totally disconnected. So not just algebraic very close, but the underlying space is going to be very close. And then you take some sort of algebraic version.
then condition.
And then Kaizen.
So what is the Rham stack of CP?
So this is exactly what's going on. So examples of the Rham stacks. Let's do this. Here, the rest of the talk will be about examples. So, yes. So, what is the Rham stack of CP? Well, CP is the uniform completion of QP bar. That we agree with that. And QP bar is a colimit of étal QP elements. This is a way to say that, but it is correct. It's just a colimit of an extension, and this one is just a QP elements. So this Rham stack, because of the first point in the theorem, it doesn't care about uniform completions. So this is the same as the Rham stack of QP bar. But QP bar being a colimit of étal maps by, let's say, something similar to having for the Rham stack, that whenever you have a formally a morphism of algebras, then the Rham stack of this morphism is just itself. So there is not a Rham stack. Then because this one is, again, something that is just a colimit of étal maps, this is just itself. Being a colimit of étal maps. So the Rham stack is in some sense a way to decomplete, at least a very important way, spaces in a very strong sense, very strong sort of definition. So another example. So let me take QP, like those unit volt, but see the minimum computation. This, right? So this is a ball where you add just the additional point of infinity that corresponds to a suitable Hoover curve. So this ball in the realm of analytic geometry is just a spectrum of this ring, where again, I emphasizes that this ring has not it's just a ring over QP, a solid ring. So there is not this additional solid structure you put in order to embed adic things. So you should think about this ring as actually being QP T plus in ZP plus P ZP. So actually, this the spectrum of this adic space, which is the minimum quantification. But this ring, so.
I'm sorry, and the other one corresponds to what?
And the other one, yes, so that's a substitution mentioned. This one and the other hand corresponds to this term. So these are different ring or integral, open integral closed rings. But we have something else.
So it's not an analytic spectrum, it's not.
Let's say that you can always attach an analytic spectrum to over rings, in some sense. And the analytic spectrum of just this ring, like the underlying ring, maybe over QP solid, corresponds more to this one than this one. For this one, you need to solidify it here. An additional process. Sorry? You need to take a plus into account. So, well, we also have this overconvergent closed unit disk. And the and the sheaf of functions attached to this, the ring here, is just this ring of overconvergent functions. Previous one. So, something that you can write into it. Well, this just makes sense. So, function that overconvergent is already. But the uniform completion of this ring is just the tail algebra. So this is telling you that actually the drum stack of this closed disk is just the same as the drum stack of this overconvergent liquid. And actually, these are in space. Consider its minimal modification. Then these are the cohomology in each variant is not going to be nothing but the overconvergent drum. In particular, this would imply that overconvergent and cohomology is independent of the overconvergent structure you put into the variety.
What do you call these things minimal compactification? Just the figure of it. There's some non-minimal ones.
It's minimal in the world of Alice. In the sense that you have a map into something that is proper, that is not proper. So let me copy the compactifications.
Is that a definition or is that like
That's a fact. That's a theory.
the right hand side has some other definition?
The right hand side is maybe the rank homology of any overconvergent structure you put in X, and then you prove that it's independent of any overconvergent structure. This theorem tells you that, well, basically study this theorem.
Can I just ask a question about down to one? So, is there any more down to earth way to say what unspec of QP bar is?
I mean, it's a point whose underlying ring is QP bar. I think that more than that is, yeah, not literally, I don't know if there is a better way of talking about that. Sorry.
In that statement, is the topology on QP bar the covalent topology?
Yeah. Yes. Yeah, maybe keeping track of it. So, okay, so this is one example. So let me go back to programs. The last one. Maybe. So, perfectoid space. S can attach this thing called the Fargues-Fontaine curve, but let me consider something before the Fargues-Fontaine curve, which is the Y construction. Y curve. that if S is affinoid, let me use usual notation then. Then this thing is just with an adic spectrum of I equals to plus, but we remove the losses where P and maybe the diagonal of some segment equalizer matches. Start. S is just the ground stack of the technique. So because of all these descent theorems that I just mentioned there, by the free theorem, we can make sense of this construction for diamonds. Or any diamond. Any sense. This one. We have a stack X that is just obtained by again descent out from perfectoid.
The any actually mean? Maybe you said this already.
Any means diamonds you can access using these kind of equivalent relations, but you don't care about that class. So it mostly the Markovitch like sense.
For that, you just need to work out the seven.
For that, you just need to work out descent, but maybe that version of yeah. Usually for all diamonds, you need a work out descent. Maybe you just so far can do this kind of products. So for example, pro-analytic descent, right? Countable limits. So that's sorry for having this part. We do the last example, or we just want to finish with that. Is that let us take S to be the spectrum of a P of P infinity or P infinity. Then I infer of S is actually isomorphic to it. Well, the ring is about 150, like just this perfect delta ring. And recall that we started, so we had this ring at the beginning and all with a Frobenius. Any Frobenius. So this ring you can also write it down as the limit, whole limit, by Frobenius of this ring, no matter which Frobenius, after you take some sort of uniform completion, in this case particularly speed each completion. So the curve T is X first. Right. And what T, yes, when it's X and Y is X, okay? X is the limit, in this case more not in the categorical sense, but literally just the limit of the Frobenius minus N T over T. Usually you take us the sequence of elements having inputs. So the curve is obtained by taking this space and removing P and the type Euler of the segment of myself. So actually, this will tell you that you will have a map of this curve to the limit Hadam Frobenius of the open unit disk. So this corresponds to removing the locus of base to 0, making P smaller than P to the epsilon for some epsilon. And then you want to remove the segment from myself of X. But like this formula tells you that when you remove X, what you remove is just the intersection of all the things. So you're removing the deal of the inner vector. This guy is the uniform completion. So again, if you take Rham stacks, if the Rham stack is just the limit of the Rham stacks, this guy, minus this kind of big ones.
So when you take all that into account, you're just getting the divisor of log 1 plus t, right?
Yes.
So you're sort of allowing log pulls.
Yes. So in the case that you take a synchronous prism, just taking the value 1. In the case of the Freud kissing delta ring, you're removing 0. So like what corresponds to 0 here, and the other one corresponds to the sequence of ones. So this tells you that, well, again, like this guy is some sense one for convenience. Having a vector bundle in here is the same as having a pi nabla module over the rubber ring. Well, of course, modulo actually extending this to the whole ring and passing to this space, but it's the same category. And it tells you that this category of nabla modules, pi nabla modules over the rubber ring, over any rubber ring, is just the same as the category of vector bundles over this particular curve. And well, I think I'm already over time, so let me just mention, just saying some words, things you can do with that. So using the theory of Banach-Kolbe spaces for perfect rings, and this equivalence here, or maybe more like this translation given by that, you can reprove by purely perfect methods the statement that I mentioned at the beginning, is the p-adic theorem. Something you can do purely by knowing the study of the Banach-Kolbe space on perfect rings, which let's say is one of the critical parts also in the work of Kedlaya in his book of the p-adic theorem, actually constructing a theory of slopes and higher-dimensional filtration for pi nabla modules. So in particular, vector bundles in here are some geometric version of pi n modules. So if you start, I say that you can do this for any diamonds, in particular, you can do this for any grid space. And I think the expectation we have is that if you take grid spaces and you take cohomology of these things, maybe after module of Frobenius, you should recover in one hand this Fargues-Fontaine de Rham cohomology of Bras-Vezzani and Bosco, which is essentially what you like to do, just Rham cohomology the Fargues-Fontaine stack. And second, once you translate these to pi modules, hopefully you should be able to recover your Yodokato homology of Kolbe's and Sio, in the sense that you get some vector bundle D model here, and then you translate to the pi module, which is the kind of target you get in Yodokato. So let me finish here. Thank you for your attention.
I have a question about the theorem that you wrote earlier about relating this to some category of modules over a string of infinite order differential operators.
Yes.
So if I wanted to compare that with something more classical, like a sheaves on the rigid space with an increasing filtration by coherent sheaves and a connection satisfying Griffith's transversality.
Yes.
Is that a full subcategory of what you were talking about?
No, the one that you're saying is more like a filter version of that. So there is the Rham stack, and you can make a filter version.
Is there a forgetful functor from that category to your?
Yes, so this category of Dika modules, it contains all, let's say in some sense, it is contained in algebraic D modules you can make out of a grid space, and it contains all flat connections.
So it is a little bit weird that if you change Frobenius, in one case you remove just one point, and in the other case you remove all the translations. And
I mean, in some senses, because you're taking Frobenius, and in the kind of coefficients we're doing is, again, like Frobenius equivariant, like Frobenius is an isomorphism in the type of nabla modules. So at the end, like the pi module only depends on its perfection, and the completed perfection of all these rings is the same. So I think that more explains why, except that you still need to somehow justify the completion, which in this case is because of this strongly on the process.
If you replace S with like the diamond of QP, then amounts to doing a descent along this gamma cover, right? And so now you get gamma equivariant
Exactly.
objects.
Exactly.
I have a question about the example one up there. So I think you mentioned earlier in your talk, you can also think of these maybe or in another talk I've seen you give anyway. This de Rham stock, and then you can also think here as sending like x of r is like x de Rham of r is x of r reduced.
Yes. Yes. Okay.
Reduced
So
means something more specific. But wait, so this okay? That's still true. That's right.
that's the same difference.
Okay. So then the question I had is, so in this first one, okay, we sort of see this like for example, if I sort of apply that to like b plus de Rham mod t squared, like I'd sort of have a map from n stack of CP, but I wouldn't have a map of CP. So I could sort of like, can you just like write down enough like test objects to see that you really just get n stack of QP bar
So
there?
let me tell you what is explaining this behavior.
Yeah, okay.
So Sean's question was, okay, the definition of this de Rham stack, the original assumption is like you take X and you evaluate in a ring, and each of the values very long. This is a simple definition. You have X from rings sets, let's say for X and by variety, and you map a ring R to X of the reduction. That's his definition of the Rham stack. So the analytic de Rham stack, there is some category that we call bounded rings, which is some category where you can make sense of a function being of norm less than 1, less than something. All functions are bounded, in the sense of have a norm is bounded. And then the Rham stack counter to this, maybe because we're derived to anima, but because good sets and it's not a very helpful function. And it's going to map here to the points of R in some kind of reduction of this, but something that we call this Dagger reduction. So it's with us. It's like this, giving the important elements. Or this version is are giving elements of norm 0. Which is stronger than important elements. But the caveat this is that in this suitable category of spaces, so in a suitable category, C, and let me just see separable rings. So some notion that kind of just tell you that up to uniform completion everything is countable, mod P or something. So the contour that maps something to this reduction, and the contour that maps something to this uniform completion, they are locally for this topology when it starts. But second, when it starts. Second. It means that you can always find, like, after doing shiftification, you can always find a cover of this ring for which the reduction is the same as this uniform completion. So this is kind of the strong sort of statement that allows you to, at least once you shiftify in this category, just be complete, sort of because of this feature here.
So you're talking, I guess, one upshot is that you can define P models for like diamonds.
Yeah.
And is there a Riemann-Hilbert correspondence with like Lewis-Man stuff that you mentioned?
That's a very good question. I still do not know what should be the correct statement for Riemann-Hilbert correspondence. That's it. Okay. In some sense, there is also a complex version of that, which is explaining Scholze's lecture on real finance. And I will say that, in some sense, the Riemann-Hilbert correspondence is precisely this one. In the sense that it tells you that the Rham stack for a complex space only depends on the underlying topological space and the abelian sheaves of this. The direct category is all abelian sheaves. And it follows from this part, in some sense. So this is maybe not a good answer for this setup, but at least this statement is what implies the Riemann-Hilbert corresponds to the complex space.
Do you conjecture that you can embed Lucas's category into your category or
no, Lucas category is not going to be embedded there. And also not a version with Arthur and Johannes. Instead, at least for smooth release spaces, the category that they define is going to append into the analytic personalization. At least some piece of analytic personalization, but not this piece.
no more question, let's thank the speaker again.